Hello and welcome. In this video, I'm going to be running through the 4 solutions to this sample paper that I created. If you haven't already downloaded it, there will be a link in the description that will take you to the PDF for this sample paper. And this is a sample paper to help with preparation for Unit 2 of the IGCSE in Maths, and this is for the modular pathway. And for Edexcel, for IGCSE for Maths for Edexcel Unit 2. At the minute, this course is actually new, so there is the official sample paper that Edexcel released. I've also done a previous video on that, which I'll also link down in the description. And this is like an extra sample paper that I created to help with revision. Little caveat here, creating this paper was maybe slightly more difficult than creating the papers for the Unit 1, in being that I'm not quite sure how much of Unit 1 they will put into Unit 2. There are some places where Unit 1 and Unit 2 kind of naturally overlap. For instance, you will see that there is a little bit of indices in here. There is a completing the square, and this kind of stuff like completing the square was listed as one of the topics in Unit 1, but I'm assuming that Edexcel could still test you on this. If you look at their official paper, they did have a question still in there on indices. So yeah, it's hard to tell quite how much overlap there will be or how much stuff that you could expect to come up from the Unit 1 stuff. So outside of using this paper, I'd probably just recommend that you use full normal IGCSE papers, and then just kind of try and focus on the topics that are the ones for Unit 2. But yes, just bear in mind that I don't see any reason why they can't throw in some indices and stuff like that from Unit 1. Okay, so I did focus mostly on the Unit 2 stuff. As I said, there is a little bit of overlap in there as well. And then for this first question, this is a shape transformation question. With this is quite hard to kind of show you on the computer screen how you would do this. The best thing to do is to print it out and do it yourself, because you are probably going to want to use tracing paper. So you are rotating triangle A 180 degrees, about 1 minus 1. So you are going to find 1 minus 1, which is there. You will mark that on with a cross, and then you are going to take a sheet of tracing paper. This blue box is my pretend tracing paper. You will put the pen on the cross there that I've marked out, and then you are going to draw over the shape onto the tracing paper, and then you will turn the tracing paper. Now in this case, because you're turning 180 degrees, if you turn it 90 degrees, it will flip this way, and then you're going to turn another 180, and it doesn't matter which direction you go in. And then when the shape appears, you will draw your shape onto the paper, and you should have done it here. Minus 1, minus 3, so that would be one vertice. Minus 1, negative 4, that would be another vertice. Minus 1, minus 3, minus 3, that would be another one, and then the triangle will be drawn here. As I said, it's quite hard to demonstrate how you do that exactly. You want to use your tracing paper to do it, and it's asked us to label the new triangle B. Okay, for the second part B here, you want to translate the triangle A by the vector minus 7, 3, label the two new triangles C. So let's look at triangle A. This is easier to do on the screen. You're going to choose one corner, so I'm going to choose this top corner here. And then I'm going to move minus 7. This is in the x direction, so I'm going to count 7 squares. 1, 2, 3, 4, 5, 6, 7. So we're now here. And then I'm going to go up 3. This is in the y direction, and it is positive, so we move up. So this is 1, 2, 3, and so my new corner appears here. And then you can go ahead and draw the triangle exactly as it is down the bottom. Okay, now we need to label this triangle as well. I'm going to label this triangle here C, and we are done. Okay, on to question number 2. This is a highest common factor question. If you're given a HCF or an LCM question, the smartest thing to do is to do the prime factor decomposition. So I'm going to take 72, and I notice now that's divisible by 2. It is 2 times 36. When you hit a prime, you circle it. If it is not prime, we continue. So 36 is 2 times 18. 18 is 2 times 9. Now, 9 is still not prime. We can divide 9, not by 2, but that is 3 times 3. Both of those are primes, so then we stop. Then for 108, I'm going to do exactly the same thing. So 108 is also even, so I can divide that by 2, and it is 2 times 54. 54 is not prime, so we continue. 54 is 2 times 27. 27 is not prime. 27 is 3 times 9. 3 is prime, so we stop there, and then 9 will be 3 times 3. Then some people use a Venn diagram. My students don't usually like the Venn diagram, so I just do like a listing method. I'm going to write out the prime factor decomposition of 72 here. So this is 2 times 2 times 2. I'm just doing these 2 times 2 times 2, and then times 3 times 3. So I just write them all out. I usually do them in order. It's not necessary, but it will help you kind of, it will help you with the problem and keep everything neat. So the 108 is 2 times 2. Let's both of these down, and then I have 3 3s. So it's times 3 times 3 times 3. And you'll notice I left a gap there, and that was to keep the 3s below the 3s and the 2s below the 2s. It'll just make things a bit easier, because now I'm going to identify pairs, and I can see I have matching 2s here. I have matching 2s here. This last 2 doesn't match with anything, but these 3s form a pair, these 3 form a pair, and then I have 1 3 on the end here. Now for the highest common factor, we're going to multiply together everything that's in those bubbles. So this is 2 times 2 times 3 times 3. And you can go ahead and type that in your calculator, and you'll get highest common factor of 36. Okay, here we have some similar shapes. This is a very simple similar shapes question. You'll see later on in the paper there's like a similar area, similar volume. Here you have two triangles, and first of all it's asked to calculate the length of BC. So be careful here. I'm looking at for BC and I'm noticing it's this side here. I think it'd be very easy to think that maybe they want you to find the ones that are labelled X and Y, but they haven't. It's this one. First of all, we need to find some sides that allow me to work out what we have multiplied by. And I can see this AB side is going to match with the PQ here. So from 4 to 12, that's kind of like the same side on the shape, and that's been multiplied by 3. So from the smaller shape to the larger shape, we're timesing by 3. This we are going back the other way, so we are actually going to have to divide by 3. So I'm going to do 16.5 divided by 3, and that is 5.5. Okay, the second question, write down an expression for y in terms of x. So y in terms of x means we want y is equal to something. So let's look at y. Okay, y is on the big triangle, and then that corresponds to x over here. And going from big to small, we are going to divide by 3. Or if I want to get y from x, we are going to multiply by 3. So I want y is equal to, and so y is equal to 3 times x, or 3x. Okay, now we have some inequalities here. So first of all, they've asked us to draw these lines out. So y is equal to 2. Be careful here. You look for the y-axis, which is this one. We go down until we find 2, which is here. And then I draw a line across there. So y is always 2. X can be any number. And then x is 6. Again, I find the x-axis, which is here. I find 6, which is here. And then I'm going to draw this straight line on. You guys will obviously use a ruler. We are done. And then I have y is equal to x plus 1. This is slightly more harder, I guess. So we're going to do x and y. And let's put in some values. So let's pretend that x is 0, 1, and 2. Well, y is x plus 1. So 0 plus 1 is going to be 1. 1 plus 1 is going to be 2. And then 2 plus 1 is going to be 3. And then I can plot on these coordinates. So if x is 0, y is 1. If x is 1, y is 2. If x is 2, y is 3. And now I can see what this line should look like. It's going to be a diagonal line crossing through at 1. Now I've been asked to also label these. Let's make sure I've got those labels on. This was y is 2. This line here is x is 6. And then this line here is y is x plus 1. Okay, show by shading on the grid the region that satisfies all three of these inequalities. I'll give you a little tip here. I'm quite certain, without even looking at it, that it's going to be this shape here. It's usually the area that has been naturally bounded. You can see that kind of triangle shape that's been made by the lines. It's very unusual that you have something like down here like this, for instance. But we will just check that my hypothesis is correct by actually looking at the inequalities. So I want y is greater than or equal to 2. So I look for the line y is equal to 2, which is here. And I want greater than, so I need to go more, which means we are going above. And then for x is less than or equal to 6, I look for that line that's here. X is equal to 6. And I want less than, which means we're going to the left this way. And then I lastly want y is less than x plus 1. Here is the line y is equal to x plus 1, and less than means we are going below the line, so down here. And so I can see indeed that has formed this triangle shape here. That's what I want to shade, and it tells me to label as well. So I'm just going to try and put an R in there. Okay, question number 5. The bearing of Paris from London is 149. Work out the bearing of London from Paris. This is a great example of what I was saying before about I'm cautious about how much of Unit 1 will be in Unit 2. Bearings often, so this is quite an easy bearing question, but often you will get bearing questions and they will have 3 points A, B, and C, and they will involve a triangle, and then you will end up doing sine and cosine rule to find angles in the triangle, to find bearings, or even to find distances. So often bearings are mixed up with sine and cosine rule. So it's a good idea to go and look at some of those questions as well, just in case they throw in a bearing question that also uses sine and cosine. But this is just a straightforward one, just with bearings. So I'm going to draw in Paris here. The bearing of Paris from London. Oh, okay. So the from there is before the London part. So actually my bearing is starting off with London. So I'm actually going to change that to London here because I want to start from London. Now I'm going to consider this bearing as 149 degrees. So that is about 90 degrees. That is about 180. So I want to be between those two. Doesn't really matter, to be honest, what your drawing looks like, but I find it helpful if it is roughly as you would expect. I'm going to draw another line for north. This is now Paris. And so what they want is to work out the bearing of London from Paris. So this is 149. This time they want to go from Paris. So what they want is this angle here, clockwise from north around to that kind of like travel line between London and Paris. Now we're going to use angles in parallel lines because if you have two parallel lines like this and a line going across the middle, these two here will add to 180 degrees. So that means I can do 180 minus 149. That would get me this angle here. And so that is 31. And then remember, angles are a circle of 360. So I'm going to do 360 degrees minus 31 to get that big angle on the outside, which is 329. Okay, now we have a baker. She is using 120 grams of sugar. I want to know the weight of flour that she uses. So here we have flour to butter. Here I have butter to sugar, and I'm told the weight of the sugar. So what that means is that this part here, sugar, is 120 grams. Now the 120 grams needs to represent two parts, at least in this second ratio here. I'm going to do 120 divided by 2 to get one part. So one part is worth 60 grams. Now I want to go to the flour, but I think I'm going to have to use that butter as kind of like a stepping stone. So if one part is 60, and I can see here the butter is worth 3 parts, I'm going to do 60 times 3 to see how much butter she used, and that would have been 180 grams. So now I have the butter part as being 180, and I can see from the flour to butter ratio, 180 is now 5 parts. So I do 180 divided by 5, and that is 36. And then I am now going to work out how much flour we used. I know that 1 part now is 36, but we use 6 parts of flour. So I do 6 times 36, and that is 216. And we can move on to our next question. So for question number 7, this is a kind of mean problem solving question. So we have 4 bananas. The mean weight of the 4 bananas is 145 grams. Well, how do we work out mean? We must have taken the total weight of those 4 bananas and divided through by 4, and then that answer was 145. So now I can work backwards and see what was the total weight of all those 4 bananas. And to do that, I'm going to take 145 and I'm going to multiply by the 4. So the total weight is going to be 145 times 4, which is 580. Now I do the same for the second mean. That was for 4 bananas. Now this time I have the total of 5 bananas divided through by 5, and that gave me a mean of 142. And so again, I'm going to multiply up by 5 here to work out what the total weight of those 5 bananas was. So 142 times 5 is 710. And now we know that Andy has put 1 extra banana into the bag. So I want to know what is the difference from here to see how much he added in. So I do 710 minus 580, and that gives you 130, which is the final answer. Okay, for question number 8, we have a compound interest question. So when you're working out compound interest, you take the principal amount, which in our case is 2,000. You multiply by the multiplier, and then you're going to raise that to the power of the number of years, which is 3. So the only thing now is, well, what is this multiplier? Now this could be, it's going to be a decimal number. It will be something like 0 point something or 1 point something usually, and you're going to use this percentage here to work it out. So she gets 4% each year compound interest. So this means we are increasing by 4%. So I take the 100% and I add on the 4%, and that gets me 104%. So every single year she's going to have 104% of what she had the previous year. Now we do not want this as a percentage, we want it as a decimal. Now 104% is the same as 104 over 100. This is it as a fraction. Yes, you can write percentage over 100 to get as a fraction. So you're doing 104 divided by 100 and you'll get 1.04. This becomes the multiplier. So you're going to do 2,000 times 1.04 to the power of 3. We want the answer to the nearest dollar, and to the nearest dollar that is 2250. Okay, this is a little bit different because now we have a decrease. It decreases by 9% each year. We're going to need that multiplier again. So this time I'm going to take 100% and I'm going to minus 9%, and this gives me 91%. So what this means is that Sam's investment is going down 9% each year. So every year he has 91% of what he had the previous year. Now again, for a multiplier, this is the same as 91 over 100. You can do that on your calculator, and that's 0.91. This is like the multiplier. Now, this time is a little bit more complicated because he invested T, and at the end of the first year, his investment is this. So T is his investment times the multiplier, 0.91, and actually it's only at the end of the first year, so the number of years is just 1 in this case. And then at the end, he has $1,365. So in order to work backwards, we are going to take 1,365 and we are going to divide by 0.91. And if you take 1,365 and divide by 0.91, you will get 1,500. And so that is his investment. Okay, moving on to question number 9, we have a standard form question. So 8.4 times 10 to the minus 5. If this number here is negative, the decimal point needs to move over to the left. If it was positive, it would move in the opposite direction. And the decimal point is going to move over to the left 5 times. So we can write ourselves out some extra zeros and just count. So let's move once, moves twice, moves 3 times, 4 times, 5 times, so it's going to end up there. Yes, and I could have put in some more zeros if I needed, but luckily I did enough. And you might also notice, well, actually you've written up 5 zeros. 1, 2, 3, 4, 5 zeros there, which is the same as the number on the decimal, and that will always work. However, it does not work for positives. So when you increase, it's a little bit different. So that's why I do still, when I'm explaining how to do it, do the counting method of moving the decimal place that number of points. So 0.000084. Now work out this, we're multiplying two things together, and you'll notice here these numbers are really big. If you look at some older kind of like IGCSE papers, they did usually do small numbers for these kind of calculations, but I think the examiners have realised that when the numbers are small, it's too easy to do on your calculator, and you don't actually have to calculate. Here for the big numbers, we cannot do it on calculator, we will need to calculate, so I'm going to do 6.5 times 10 to the minus 40 times 8 times 10 to the 185. Now, when you're multiplying things, it doesn't matter what order you multiply in. So I am going to take this 6.5 and I'm going to times it by the 8 first. And so if you take 6.5 and multiply up by 8, you get 52. And so this is 52 times 10 to the minus 40 times 10 to the 185. Now, when you are multiplying together things that have indices, remember you can just add these indices. So we are going to add this with this. And so minus 40 plus 185, or 185 minus 40, you can do that on your calculator and you will get 145. So this is 52 times 10 to the power of 145. And so this is looking pretty good now. You might think that you are finished. However, this is not yet in standard form. So in standard form, the number always needs to be less than 10. Yes, it should be more than 1 and less than 10. Our number is over 10. So we actually want to write this as 5.2 times 10 to the power of something. Now, because on this side I have divided by 10, so a decimal point was here, and I've divided by 10, I need to multiply by 10 onto the other side in order to keep the balance so that it is the same number. Now, if you take this thing here and multiply by 10, then the indice just goes up by 1. So we divide the 5.2 by 10, I times the 10 to the 145 by 10, and so that becomes 10 to the 146. I just add on 1 power of 10. Times 10 to the 146, and we're done. Okay, so this is an angle in polygons question. At the minute, we have not been given any angles at all, so I'm going to work out what they are. I know that I have a regular pentagon, so this shape on the left here is a 5-sided shape, and a regular hexagon, so the shape on the left is a 6-sided shape. Now, the first thing I want to do is to check what angle I'm finding. And this is marked on, so it seems to be that one at A, but I'm just going to double check. Work out the sides of EAF. EAF, yes, it is the one they've marked on there for us. So I think if I can work out the interior angles of this polygon, that's going to help me at this point here, E. If I can work out this angle and I can work out this angle, I can see what's left, and I can work out this angle. So let's go ahead and do that. We have a formula for interior angles. So the sum of the interior angles is given by the number of sides minus 2 times 180. Minus 2 times 180. 5 minus 2 is 3, and then if you take 3 times 180, you will get 540. And this is the sum of the interior angles. So this is for the pentagon. This is the number of sides here, n. And so what it means is that all of these added together sum to make 540. I want to know what one angle is though, not all of them added together. And luckily we were told that this shape was regular. Because it is regular, that means that all of those angles I've marked in blue are exactly the same size. So I can do 540 and divide through by 5 to see what one of them should be. And 540 divided by 5 gets me to 108. So I'm going to rub out these, and I'm going to say that this angle here is 108. I'm going to do the same thing for the other shape. So the other shape is a hexagon, so a 6-sided shape. So I take the number of sides, I subtract 2, and I multiply by 180. Now when you do that in your calculator, you will get 720. And remember, this is the sum. So this is all of these angles now added together, total to 720. But we have the same thing again. It's a regular hexagon. So I can do 720 and divide that through by 6. And I will get 120, which means that this angle here is 120. And I can go ahead and rub all the others out because I'm not interested in these ones. So now what I actually want to get is this angle here. And because those form a point, I can do 360 minus 108 minus 120 and see what is left, and that would be 132. That means this is 132. Now, it might be difficult to see where we are going to go next, but next we're actually going to use the fact you can see that these two shapes join at this side here, ED. So they're both regular, and they also both have the same side lengths. Yes, because that side at ED is for both of the shapes. So what that means is that all of the sides all around the edge are all the same, and so what that means is that these two sides here are also the same. So because those two sides are the same, we now have an isosceles triangle. So I can do 180 degrees because there are 180 degrees in a triangle. I subtract 132, and that is 48. And then because it is isosceles, it means this angle at A is exactly the same as this angle at F, and so I can take 48 and divide that by 2, and I get 24. And so the size of our angle is 24. We can write that in on a dotted line, and we are done. Okay, this is a cumulative frequency table. First of all, they ask us to work out the cumulative frequency. So the cumulative frequency means that you add all of the previous frequencies. So between 0 and 1, we have 4, weights of parcels. So between 0 and 1 kilogram, there are 4 parcels in that weight. And so I can put that here. And then the next category is between 0 and 2. So it should be all of these and all of these. So you add those two numbers together and you will get 19. The next category is between 0 and 3. So I need to then add on the 20. 19 plus 20 is 39. Oh, not 32. 39. Then we're going to add on the 11. And so this is 50. And then 50 plus 6 is 56. And then lastly, 56 plus that 4, the 4 heaviest parcels, gets us to 60. And then I'm just going to double check at the top. They often give you the total. So you can see there was a total of 60 parcels. So if I didn't get to 60 there, I knew I would have made a mistake, but we did, so no problem. And we can move on to drawing our cumulative frequency graph. So on the grid below, draw the cumulative frequency graphs for your table. Now, at the first point, we have a cumulative frequency of 4, which is here. That's where I'll find 4. Now, where am I going to draw my cross? Because this is actually a range. So you'll see that the weight in kilograms between 0 and 1 has a cumulative frequency of 4. So some students will make the mistake of sometimes doing it at 0.5 in the middle. Actually, you always want to take the upper bound because it's cumulative. So what we're saying is that once we get to 1 kilogram, we've definitely had 4 parcels. Once we get to 2 kilograms, we've definitely had 19 parcels, and so on. So we always take that upper bound. So at 1 kilogram, 4 parcels. Once we get to 2 kilograms, we've had 19 parcels. Once we get to 3 kilograms, we've had 39 parcels. Once we get to 4 kilograms, we've had 50 parcels. 5 kilograms, we've had 56. And then 6 kilograms is all of them as 60. And so this does kind of take the shape that I'd expect. I think on the sample paper that Edexcel was kind of a weird looking cumulative frequency, but this is as you would think. And it's nice to draw a smooth curve, although I think for these kind of questions, if you do a dot-to-dot method, you don't lose marks. But usually best to do freehand and just as good as you can, like that was not amazing. Just as good as you can, try and make it look a little bit like this kind of curve shape. Okay, use your graph to find an estimate for the median weight of the 60 parcels. So the median is going to be in the middle. So what we are asking is how heavy is the 30th parcel? And the 30th parcel is here, given to frequency 30, and you draw a line across, and you should actually, you guys obviously will use your ruler, as I said, and you should actually keep that line on there. So draw that line on your graph and leave it on so your examiner can see what you're doing. And then I get 2.6, although there will be a range that you can have. Use your graph to find an estimate for the number of these parcels that weigh more than 3.7 kilograms. So kilograms now is down here, so I'm looking on this other axis, and I want to find 3.7. 3.7, let me check, yes, 3.7. And so I'm going to draw a line up here. That is where 3.7 is. And again, not having a ruler is making my line look very wonky. We should go up to there. And then along to here. And I'm making that to be 57. Now, it might be tempting to say that 57 is the answer. 57 is not the answer because we want the number of parcels that weigh more than 3.7 kilograms. And actually, 57 is the number of parcels that were 3.5 or less, because that was what the cumulative frequency was doing. It was adding up everything that weighed less. So to find out how many parcels weigh more than 3.7, I'm going to take the full 60 parcels. And I'm going to start, sorry, there's a mistake there. Apologies, that is not 57, that is 47. So I'm going to take all 60 parcels, I'm going to subtract 47 from it. So I was reading the scale incorrectly. And so 60 minus 47 is 13, and I can write that number on the dotted line. And again, there will be a correct range that you can use here. In this case, I think the mark scheme wanted an integer answer. So if you put 13.5 or something like that, you're going to lose a mark. They wanted the number of parcels, and they expected that it would be a whole number of parcels, not half a parcel. Okay, so here we have a circle theorem question. We want the sides of angle ABC. So let's find that angle. ABC is here. That's ABC like this. Now this shape looks a little bit confusing, and I want you to imagine that this point here at B can move. Imagine that's flexible on the circle, and imagine you drag it out in this direction. And if you do that, drag it out in this direction, you will get something that looks a little bit more like this problem. Do you see? This is like the A and the C, and now the B has been dragged out over here like this. And so it's the same as this kind of arrow problem, and the angle at the center is twice the angle at the circumference. That's the problem we have. In our case, the angle at the center is here. So if I can work out that angle at O, then I can say the angle at B is half as much. And we can use that 52 there to work out the angle at O. So I'll draw that on my kind of diagram that I've manipulated. If we make this triangle here and I say that this is 52, well, because this is the center at this point, these two are radiuses, and so we have another isosceles triangle. So what that means is that this is also 52 here. So I'm going to start off by doing 52 plus 52 to see the total of those angles, and that is 104. Then I'm going to do 104, sorry, not 104, 180 minus 104, because angles in a triangle add to 180. 180 minus 104 is 76. And so this is this angle here in the middle. This is 76. This is 76. And then, as I said before, once we've got that one, we can say that the angle at B is going to be half as much. So I'm going to do 76 divided by 2. And that is 38. And we are done. The answer is 38. This angle is 38 in my strange drawing, and this down here I can say is 38. Now, we have not got all the marks because it asked for reasons for our working. So we've probably got either 1 or 2 marks out of the 3. It's best to give a reason for all, although they usually are generous. Maybe definitely the last point will need a reason. So the angle at the centre, angle at the circumference, but probably either one of the 2 triangle rules will do. But I will fill them all in. So each line of working hopefully should have some kind of rule attached to it. And for the first one, we are going to say base angles in an isosceles triangle so feel free to play me at double speed if you are watching, are equal. Right, that's my first point. And then my second one here, so 180 minus 104 is 76. What I'm using there is angles in a triangle add to 180. And when you're doing these reasons, you don't really need to worry too much about spelling or the exact wording that you've used. Although I think, to be honest, it probably is easier to remember these rules off by heart than it is to kind of write them yourself out of your head. And so for the last one, it is angles at the centre. So we probably don't need the S there. The angle at the centre is twice. Oh, definitely should be a C. Is twice the angle at the circumference. Okay, and we're done. That's our reasons. 13, make x the subject. Okay, so we're trying to rearrange for x. The first thing I want to do is get rid of that annoying root. So I'm going to square both sides. So I have y squared is equal to, and then if I square this, I will just have 2x plus 1 over x minus 1. Then anything with a fraction we do not like, so I'm going to multiply up by that fraction there. What's on the denominator will get multiplied over here. So I'm going to have y squared times x minus 1 is equal to 2x plus 1. Now at this point, this is probably where I'd start looking for the x's, because essentially, because we want to make x the subject, anything with x needs to be on one side of the equals, and I want all the x's on one side, and I want nothing other than x there and no x's on the other side. They want to be completely separated. And at the minute I can see I've got x's on both sides everywhere. I can't really separate up this left-hand side without expanding this bracket. So I'm going to have xy squared minus y squared is equal to 2x plus 1. Now I see I can start getting those x's by themselves. So I'm going to leave the xy squared where it is. And I'm going to take this minus, so it's 2x onto the other side, so it'll become minus 2x. And then I'm going to leave the 1 where it is, and then I'm going to take this y squared onto the other side, so it'll become plus y squared. And so now you can see everything that has x in is on the left, everything on the right has no x. Now we factorize x out of the left. So I have x y squared minus 2 is equal to 1 plus y squared. And then lastly, I can divide through by that bracket. And so I have x is equal to 1 plus y squared over y squared minus 2. Oh, so 2. And we are done. X is the subject, and then this thing wants to go into this line, the full equation with the x on the left and then the fraction on the right. Okay, our next question, number 14, we have a chord problem here. And what I'm going to have to use for these intersecting chord problems is that this, PT, multiplied by this, is equal to this multiplied by this. And I can immediately see, using that rule, I should be able to work out that PT part because it's the only bit that is missing for me. So I'm going to write 4 times 12 is equal to PT times 3. 4 times 12 is 48. So 48 is PT times 3. And I'm going to divide through by 3. And I have PT is equal to 48 divided by 3, which is 16. And so this here is 16. Okay, now that wasn't actually what the problem asked. I think the problem asked for the radius of the circle. So PT is not necessarily the radius. But if I look back in the information, it tells me PTQ is the diameter. PTQ is the diameter. PTQ is equal to 16 plus 3. Full length along, so that's 19. This here is the diameter. And so to work out the radius, I'm just going to divide that by 2. 19 divided by 2, which is 9.5. Or if you've written that as a fraction, that's also going to be fine. Okay, here we have a proof question. Prove that the sum of the squares of any two consecutive odd numbers, when it's divided by 8, the remainder is 2, show clear algebraic working. So often for these kind of proof questions, they use either odd or even numbers, and you need to know how to define them. Even numbers we do not need, but even numbers are 2k. So this is the definition here of an even number. K could be any number. If you take any number and multiply it by 2, then you know the result is always even, and every even number can be expressed this way. 10 is an even number, which is 2 times 5. This is all the evens. But for the odd numbers, we don't actually want 2k, you want 2k plus 1. So an odd number is 1 more than any even number. And we want 2 consecutive odd numbers. So what is the next odd number after this one? It is going to be 2 more. Yes, if you take an odd number and you add on 1, you'll get back to an even number. But add on 2, you get to another odd number. So this is going to be 2k plus 3. These are 2 consecutive odd numbers, 2k plus 1 and 2k plus 3. You could also have done 2k plus 1, 2k minus 1, that's fine. So prove that when the sum of the squares, so I need to square both of these and add them together. So 2k plus 1 squared plus 2k plus 3 squared. So let's square out that first bracket. This is 2k plus 1 times 2k plus 1. So what you're doing is this. You're expanding out this bracket here. You can use FOIL, you can use smiley face, or you can use a grid, whatever you like. And you will get 4k squared plus 4k plus 1. That's the first set of brackets, and then we're going to expand this, and this is 2k plus 3 multiplied by itself. And again, you can use smiley face or FOIL or a grid, and you will get 4k squared plus 12k plus 9. Okay, now we've done our expansion, we can start to collect some of these things here together. So I can see I've got 4k squared plus 4k squared, well that's 8k squared, 4k plus 12k, which is 16k, and then 1 plus 9, which is 10. So this is the sum of 2 consecutive odd numbers. Sorry, the sum of the squares of 2 consecutive odd numbers. Now what I want to consider is what happens when it's divided by 8. I want to show the remainder is always 2. And so what we're going to do is we're going to factorize 8 out of this. So I want 8, and I want to open up some brackets. Now if I divide the first term by 8, I'm going to have k squared. If I divide the second term by 8, this is divisible by 8, so 2k. Now the last term isn't divisible by 8, and this is where the remainder 2 part comes up. 10 can be written as 8 plus 2. There's an 8 in there, but it's 2 more than a multiple of 8. So if you factorize the 8 out of the 8 part, you've got plus 1, and then 2 left over. Yes, and you can just expand this back out just to kind of check what happens when you expand. Well, you would get 8k squared, that's the same as this, 16k there, that's the same as that. And then this would be plus 8, and then you'd have this extra 2 on the end, which would bring you up to the 10. So we've factorized 8 out, and we've left 2 outside. And this was pretty much proven it, right? I can see now k is an integer, and so therefore this thing here is an integer, the bit in the brackets. And if you multiply an integer by 8, it's definitely a multiple of 8, and then if I add on 2, it is 2 more. So if I take this whole thing and divide it by 8, the remainder would be 2. My examiner won't think this is enough. We need to write a conclusion, and I'm literally just going to write out kind of what I said just then. I'm going to say 8k squared plus 2k plus 1 is a multiple of 8. Of 8. And so therefore we have 8k squared plus 2k plus 1 plus 2. This must be 2 more than a multiple of 8. Multiple of 8. And that will be enough for our examiner. There's usually a few different ways you can word this, and they're usually kind of generous. But you really want to make sure that like their conclusion here. So either you've said that it's 2 more than a multiple of 8, or the remainder is always 2. You kind of want to repeat the question at the bottom. Okay, 16. This is a proportion question. So when a photograph is taken, the exposure time t is directly proportional to the square of the size f of the opening in the camera lens. So we have t is directly proportional to f. And this is how we write this, the kind of like formal notation. This reads t directly proportional to f. Sorry, directly proportional to the square of f. So it should be f squared like this. You don't need to write out that first line. You can go straight into writing it as an equation. This is going to be the same as t is equal to k, which is some value that I want to work out, multiplied by f squared. Yeah, so this is the same as the thing that they've set up for us at the top. T is directly proportional to the square of f, so t is kf squared. Now we want to work out what that k is, so we can write a formula for t in terms of f, and to work out what that k is, I'm going to use this initial condition they've given us. So when t is 0.02, then f is 8. So I have k times 8 squared. So I just substitute in the t and the f that they've given us. 8 squared is 64. So I have 0.02 is equal to 64k. And then I can divide through by 64, and I get k is 1 over 3200. Now this is k, this is not the full equation, they want a formula. So I'm going to take this thing here and just replace k. So I have t is, and then k is 1 over 3200 f squared. That is the answer, that can be written on the line. Okay, calculate the value of f when t is 0.0098. So I'm going to use the formula that I just wrote out. I'm going to replace t with 0.0098. This is equal to 1 over 3200 f squared. And now we're trying to solve this equation for f. So first of all, I'm going to multiply up by 3200, and I will get f squared is equal to 784 over 25. And then you need to take the square root of this, and you will get f is 28 over 5, or 5.6, whichever one of those you prefer. Okay, question number 17. So here we have a particle moving along a straight line. The displacement, as soon as I see a question like this, I'm thinking differentiation. So usually, in fact always I think, because we haven't done integration yet, actually I haven't seen a question, they always start with the displacement here. So They give you the displacement, and then you will need to work out velocity, maybe acceleration as well. So to get to the velocity, you're going to differentiate the displacement. To differentiate, you times by the indice, and then you drop the indice by 1. So 2 times 3 is 6. I write the t, I drop the power by 1 to a 2. I repeat that process again. So I'm going to multiply by 2 here. Minus 5 times 2 is minus 10. T, I drop the power by 1, so it's t to the 1. When you get to the 6t and the 5, it's kind of its own rule in a way-ish. You are following the same pattern, but it's easier to think about it as just getting rid of the t. So if something's to the power of 1, you can just get rid of the variable t, x, whatever it might be, and we're just left with 6. If you have a number by itself that has no letters, you're just going to get rid of that number, so it doesn't exist anymore. Now also, I've written the 1 here above the t, but that's not really necessary, so I'm just going to neaten that up and get rid of it. Okay, this is the velocity. Most of the time, and indeed in this case, you will need the acceleration. See acceleration there. So to get acceleration, we differentiate again. So we follow the same pattern. 6 times 2 is 12. T, drop the power, you get a 1. Now again, we have minus 10t, which means we just drop the t, so it becomes minus 10, and then 6 will go. And again, that 1 was not necessary. Okay, now I have velocity and acceleration. Let's actually look at the question. Find the value of t when the acceleration is 5. So I need to set the acceleration here equal to 5. 12t minus 10 is equal to 5. And now we are solving this. So 12t, I'm going to add 10 over here. 12t is equal to 15. And then I divide through by 12. So t is 15 over 12. And you can leave that as 15 over 12. Actually, probably a good idea to at least simplify it. Well, it doesn't say. You should get marks either way. This simplifies to 5 over 4, or as a decimal, 1.25. And it's up to you. Any one of those answers should be fine. 1.25. Okay, so here we have some transformations. The point A with the coordinate minus 3, 2 lies on some kind of, in this case, a straight line. Find the coordinates of the image of the point A on the straight line with the equation. So this is a transformation. We need to consider what is happening. When you have something inside the brackets, it affects the x coordinate. In this case, this is outside the brackets, so it affects the y coordinate. So immediately I can see that the x is not going to change, only the y will change. So x I can fill in as minus 3. Now let's think what's going to happen to that y. We have something outside the brackets. When you are outside the brackets affecting the y, you do what you think you should do, the stuff that makes sense. So in this case, we're going to do 2 minus 3, which is negative 1. Now we have a transformation inside the brackets here. And so because we're inside the bracket, this time the y remains fixed. So I'm going to fill the y coordinate in as 2, it won't change. And the x coordinate is going to change. Now if you're inside the brackets and affecting the x, you do the opposite to what you think you should do. So right now what I'm looking at is x over 2. So that would kind of make you think that you should divide by 2. But when you're inside the brackets, you flip everything around. So instead of dividing by 2, we're actually going to times by 2. So I'm going to take the x coordinate, multiply that by 2, and I get negative 6. Okay, now this question here is actually not any more complicated. It's just worded really confusing. So you have y is equal to g of x, and then you have this point here that has x coordinate p and y coordinate of q. And we're asked to find the coordinates of the point on the curve with this equation here. Now, I think this can be a bit confusing because they've used g instead of f. They tell you that c is a constant. So c is like 5, 2, 6. It's a constant. It's a number. They don't give you that information for g because g is not a constant. G is actually relating back to this g here, which is the actual function itself. So we have y is equal to minus g. And g is the function x minus c. And so now we need to think about how this is affecting that coordinate. So in this case, we have something outside the brackets. This negative here is outside the brackets, and I have something inside the brackets, which is the c. So both the x and the c will change. Now inside the brackets is going to affect the x coordinate. Now the x coordinate at the minute is p. And remember, when we are inside, we do the opposite to what we think we should do. So we might think that we should subtract c, but actually I'm going to add c. And so the new x coordinate is just p plus c. And they don't expect you to like evaluate that or give a number. It's still going to be in terms of p. They haven't given us any more information to do anything else. And then the y coordinate is q. Now on the outside we have this minus sign, which means that any positive numbers will become negative, any negative numbers will become positive. And so this q is going to become minus q. And we are done. Okay, 19, solve a simultaneous equation. So for simultaneous equations that are quadratics, what you always need to do is substitution. So they will give you one that is linear, hopefully, usually. And so in this case, this is my linear equation. And in my case, it's actually been made pretty easy for me because they've already rearranged it into a format where I can substitute. They've told me y is x plus 2. So I'm going to put x plus 2 in here and in here instead of y, and then everything will be in x. So we have x squared plus x plus 2, because we just said that that was y, squared plus x plus 2. And all this is equal to 3. Now this is a quadratic, so how we solve a quadratic is we're going to have to expand everything, get it all on one side of the equals equal to 0, and then I'll be able to solve. So first of all, I'm going to leave the x squared as it is, and I'm going to expand this thing here. And as we were doing before, this is x plus 2 times x plus 2. And you're going to need to use the grid or the smiley face or something, and you'll have x squared plus 4x plus 4. I didn't leave quite enough space about that. But that's the expansion of that. That's the expansion of that bracket there. And then I have this bracket, and actually I can just take that away because it's adding everything. So I'm going to add x, I'm going to add 2. And this is equal to 3. Now I'm going to collect all the terms together. So x squared plus x squared is 2x squared. That's these first two terms here dealt with. Then I have 4x plus x. That's going to be plus 5x. And then 4 plus 2, which is plus 6, is equal to 3. Now, as I said before, when you're solving a quadratic, you want everything on one side of the equals. So I'm going to subtract 3 over here to get it all equal to 0. So 2x squared plus 5x plus 3 is 0. Now I need to solve this for x, and they've actually said show clear algebraic working, which means that we should not just use our calculator to solve. We're probably going to lose a mark if we do that. Now when I have this case and I'm told to show clear algebraic working, what I actually do is first of all I do use my calculator. So if you use your calculator, you'll get x is minus 1 or x is minus 3 over 2. And then once I've used my calculator, I pretend to my examiner that I did algebraic working when we didn't really. So you've got two different options. That's why I've left a gap here. This is my space to pretend like I did some other workings out. And your two options is either to factorize it or to use the quadratic formula. And you can do either. In my case here, I'm going to pretend that I factorized, but you could write out the quadratic formula here, put in A, put in B, put in C, and it will show that you did some workings out. To work backwards from the roots to the factorization, we're going to do this. So when you just have a number by itself, you just change the sign here. So that's minus, so it will become plus. So this is going to be x plus 1. When you have a fraction like this, the number on the bottom is going to go before the x. So 2x. The number on the top, you just change the sign. So that will be plus 3. That's a weird 3. Still weird. Plus 3 is equal to 0. And then it is a good idea if you're doing this method and you're not actually factorizing yourself, but using the calculator and working backwards from the roots to check that your factorization is correct, because sometimes there can be a mistake. And so you just want to check that these two terms here, the x and the 2x, multiply to give you 2x squared, which they do. And then also check that these two terms here, 1 and 3, multiply to give you that 3 there, which they do. So in my case, it was fine. The trouble comes in if you have, for instance, something like 4x squared plus 10x plus 6 is 0. This, if you do it on your calculator, will give you exactly the same roots down here, and it actually is twice as much. So what you'll end up with is you'll need to put a 2 at the front there, just to double everything. But usually it does work, as it has in our case, so it's uncommon that you'll get something like that. Or you could just use the quadratic formula if you want as well, if that confuses you, working backwards from the roots to the factorization. Okay, so I have found the values of x, I have factorized, or at least pretended like I factorized. We are not quite done because we also need y. So for each of these values, I'm going to put them back into here to work out what y is. So if x is minus 1 plus 2 is 1. And so that is the second y value. If x is minus 3 over 2, minus 3 over 2, plus 2, minus 3 over 2, plus 2, so this is going to be 2 over 4 over 2, minus 3 plus 4 is 1 over 2. Okay, so these are the two y coordinates here. And then just to make it super clear that you know what goes with what, you can write these as a coordinate, or you could kind of summarize. You could say x equals minus 1, y equals 1, and x equals minus 3 over 2, y is equal to a half, because they will just want to check that you know which pair goes together. Okay, next question. We have a cone and a hemisphere. This is like a volume and surface area kind of question. They actually give us the volume of the solid shape. So this is a cone with a hemisphere being removed, and they tell us the volume, and we want the surface area of the solid hemisphere that has been removed. So we're trying to go from volume to surface area, and then I have all of these values here given to me in terms of x. Now, you are going to have to go and look on your formula sheet whenever you get a question like this, because you have volume and surface area formulas given to you for spheres and for cones. I will start off by thinking about what the volume of this solid shape actually is. So the volume of the shape is going to be the volume of the cone minus the volume of the hemisphere. And then you're going to have to turn to your formula sheet to find the formulas for cone and for hemisphere. And you will find that the formula for volume of a cone is 1 over 3 pi r squared h. And the formula for a sphere, volume of a sphere, is 4 over 3 pi r to the 3. Now the problem is we do not have a sphere, we actually have a hemisphere. So you are going to have to divide this whole thing by 2, which is the same as multiplying by a half. So this is actually the formula that we have, like this. But in this case, this is just the formulas I've taken from the formula sheet, and so I still have r and h, but they've given us some values for r and h down here, which we'll now need to substitute in. So let's substitute in what we know about our particular shape. I know volume. Volume is 6948 pi. And so that is equal to the volume of the cone, which is 1 over 3 pi r squared. Now, the radius of the cone, this distance here, has been given to us here. The radius of the base of the cone is 5x. So I'm going to put 5x in here, and then I'm going to multiply by h, and the height of the cone is 6x. So I'm going to multiply this, so it's squared, multiply that by 6x. Minus, now I can actually expand this bracket slightly, because I'm going to do a half times 4 over 3, which is 2 over 3, pi, and then r cubed. Now in this case, for the hemisphere, this radius, just for that hemisphere, is also given to us here. The radius of the hemisphere is 2x. So this is 2x cubed. Okay, sorry if that's a little squished up there. I just want to try and get most of my working out next to the shape so we can still see the shape and the workings out as we go through. Okay, now what I want to do is expand some of these brackets. So I have 6948 pi is equal to, I'm going to leave the third as it is. I'm going to leave the pi as it is. And then I'm going to square this bracket here. So this is going to become 25x squared. I square the 5 and I square the x, multiplied by 6x, minus 2 over 3 pi, and then I'm going to cube this. So this is 8x cubed. I cubed the 2 and I cubed the 8. Okay, so I'm just doing algebra now. I'm going to carry on with my process of what can I work out. 6948 pi is equal to, now I'm going to multiply all the numbers together. So I'm going to do 1/3 times 25 times 6, because all of this here is being multiplied together. And so all of those numbers, we can just times on the calculator. 1/3 times 25 times 6 is 50. Now pi I haven't multiplied in yet. You could have done, but you would be foolish to, because you're going to start to get some really strange decimals and it's going to cancel down with this pi in just a minute. And so now I'm going to multiply the x parts together. So x squared times x is x cubed. Now let's do the same thing for the second part. So you're going to do 2 over 3 times 8. Multiply these numbers together and you will get 16 over 3. Again, pi is going to be left there to cancel in a second. And then the x cubed. Now this is the part where I would say, okay, I have pi everywhere. You could have done it further up, but I think I left it till now for clarity, because I think now it can be really clear to us that we can divide by pi, divide by pi, divide by pi. Every term has a pi in it, so it's going to divide all the way down. So now we are left with 6948 is equal to 50x cubed minus 16 over 3x cubed. Now we can collect together these two terms here. We can just add them. So on your calculator, you're going to do 50 minus 16 over 3 to see how many x cubes we have there on the right-hand side. So you have 6948 is equal to, and you do 50 minus 16 over 3, and you get 134 over 3 x cubed. And you can see now we're really close to working out what x is. So now I'm going to do 6948 and I'm going to divide by 134 over 3 and I will work out what x cubed is. So when you do that division, you will have 10422 over 67. And then the last step is to take the cubed root, and this is the point where you will run out of being able to write it as a fraction. I think your calculator will give you this just as a decimal, and so this is 5.378. And so from here, what you are doing is you are taking the cubed root of that. Right, we have worked out what x is, but the examiner did not ask for what x is. It actually asked for the total surface area of the solid hemisphere. Now be careful here. There's two things to note. Total surface area, they do not want the surface area of the whole shape, which would be a much harder problem. They've asked for the surface area of the solid hemisphere, which is this kind of like shaded section up here. Another thing to note is they did say total, and they bolded total. The total surface area of the solid hemisphere. And what they mean by that is they're saying, well, if you think about the surface area of this hemisphere here, it actually has two parts. It has the curved part, the kind of dome part of it, and then also this circular part that kind of makes the base. I think it kind of makes more sense in my head actually if I draw it the other way around. So if I have a circle as the bottom and then the curved part, and you can think about it as kind of like a dome, maybe on top of a building or something, or I don't know, half of an orange, and it's going to have that base there, the circular part, and then also the curved dome part. Okay, so at this point here to work out that surface area, this is where you are going to need the surface area of a sphere. And so you go back to your formula sheet and you find surface area of a sphere is 4 pi r squared. But we don't have a full sphere, we have a hemisphere. So as before, we are going to halve that. And then I also need to add on that base, the base area. And well, that's just the area of a circle. So pi r squared, which we cannot take from our formula sheet. That's one that we need to learn. Okay, so in this case, we need r. R is the radius of the hemisphere, which again, I can take from here. The radius of the hemisphere is 2x. And we just worked out what x was. We said that x was 5.378. So I'm going to take that and multiply it by 2 to work out the radius of the hemisphere. And you will get 10.756. So let's fill that in instead of the radius. We have 1/2, 4 pi, and then now r is 10.756 squared plus pi r squared, 10.756 squared. And then you can just run that whole thing into your calculator. Now you can type that in exactly as it is, or if you've simplified it down into separate parts, you can do as well. I think this part here is 726.911 plus the area of the circle, which is 363.456. But as I said, not necessarily split it up like that. You could just type it all in and you will get a total of 1090. And I have rounded that already to the nearest integer. And that will go all the way down here. Done. Okay, 21, we have some differentiation here to do. So we are given an equation, and first of all, they ask us to find dy by dx. So earlier on in this video, we were already doing some differentiation. What you do is you bring the indice down in front, and then you drop the indice by 1. So actually, I'm going to just write it straight onto the dotted line, I think. So this is going to be 3x, drop that power by 1, and we get 2. We go on to the next one, we do the same thing again. I multiply here. So 2 times 2 is 4. This is going to be minus 4. X, and I drop that indice by 1, so it's to the power of 1. Then for the next two terms here, it becomes a little bit different. So minus 9x, just drop the x. So this is minus 9, and the 15, any numbers, they just disappear completely. Write out my notes. And I'm also going to write out this 1. This is not necessary. It is better without, just 4x. 4x to the power of 1 and 4x, same. Okay, going on to part B, find the range of values of x for which t has a positive gradient. Gradient. This thing here, dy by dx, is the gradient function. So if they said, what is the gradient when x is 1, you would just put 1 into this function to work out the gradient. If they told you the gradient is 2, what is x? You would set the whole thing equal to 2 and solve for x. In our case, we want the gradient to be positive. So this was me also hitting a quadratic inequality in this paper. We have minus 4x minus 9, and this needs to be greater than 0. Okay, when you are solving a quadratic inequality, first of all, you consider when it is equal to 0 instead of greater than to find the roots. The roots are like the critical value where it will change from positive to negative. So minus 9. I think I've been filming this for too long now. Minus 9, this is all equal to 0. So we're going to consider when this is equal to 0, we have the same problem that we had before where it says show your working clearly. I don't really want to show my working clearly. What I want to do is just put that into my calculator and solve. And to be honest, that is what I would do in first place. So first of all, I'd put that into my calculator to work out the values of x. And you will get some horrible surd number. It will be like something with a root. It does not solve very nicely. And if you press your SD button to work out what it is as a decimal, you get x is 2.52 or x is minus 1.19 because they asked it. They said correct to 3 significant figures. So usually if I solved quadratic and I got some surd or decimal answer, I might be a bit worried that I'd done something wrong. But in this case, they said correct to 3 significant figures, so we expected it. But it has said show you're working clearly. Now, previously I said once you've worked out on your calculator, you could go back to the factorization. When it's a surd like that or like a decimal like this, you can't go backwards to a neat factorization. Do not try to say that this is do not try to say this is x minus 2.25 or x plus 0.91. We've rounded. Even if we hadn't rounded, it doesn't work. You need integers or fractions to work backwards to a factorization only. But what we can do is use the quadratic formula. So I am going to write out the quadratic formula. You can find this on your on the formula sheet as well. Minus b plus minus the square root of b squared minus 4ac all over 2a. And we're going to use this quadratic formula with the values a, b, and c. So in our case, this here is a, b is -4, and c is -9. And I'm doing more than is necessary here. You don't need to label it up like this. But what you do need to do in order to have shown your working is this bit here. You're going to write minus b. So this is minus -4 plus minus the square root b squared. So this is -4 squared minus 4 times a, which is 3, times c, which is -9. All of this is being divided by 2a, which is 2 times 3. That is enough to get you your method mark. So you could at this point go and do some like partial evaluation. Like I can clearly see 2 times 3 is 6. I can clearly see that this is going to make a +4 instead of a -4 because those two negatives will make a positive. And so you could, especially if I'd left some more space here, do some partial evaluation to show more working out that this is sufficient. What I have done here is enough to show full substitution. When you're showing your substitution, be careful to put in the brackets. If I had not done the brackets around this -4 squared, you are potentially not going to get the mark if your examiner is looking carefully enough, because technically -4 squared then would give you the wrong answer. So if you need to put those brackets in there to show that it is correct, essentially. And what you could do at this point is to actually type out this thing here into your calculator and check you get to the same answers. If you are maybe feeling a little bit uncertain as to if you've done it right, or you just kind of want to make extra sure, type it in and check you get to the same answers as you do using just your calculator solve function. Okay, so that was more for solving quadratics. Now we need to get back to the question because we haven't actually finished quadratic inequality. We found the roots. Once you found the roots, I would always, for these kinds of questions, do a sketch. Your sketch is for you to make sure that you're getting the answer correct. It is not for your examiner, so it does not need to be perfect. We have one positive root and one negative root. So I will just draw something like this. And I also need to make sure my curve goes the right way. So you could either have a happy curve or you could have a sad curve. Now in our case, we look at this number here, the a value. This is positive, and so therefore we have a happy curve, and so it was the one I drew first on the left. Okay, I did make a video as well on quadratic inequalities, so if you want something a little bit more in depth, you can go look at that. Now I'm going to label in this is 1.19, the other root is 2.52, and then I also now need to check this here, are we above or below? So here I want the quadratic to be greater than 0. This is bigger than 0, so therefore we are above the line. When is the quadratic above the line? That's here and here. And so this is for values x less than 1.19, sorry, minus 1.19, or x more than 2.52, this direction here. So you can either be outside or you can be between. In this case, we are outside of the function. And please do draw the graph like I did to work it out, because otherwise you will end up in a situation where you are just guessing. Now, another little thing to consider is they could ask you for set notation. They didn't in this case, and they very, very rarely ask you for it in set notation. So we can just write this onto the dotted line, and that is the answer. If they asked it for you in set notation, you would do some curly brackets and you would say x such that, and then I just write out that first inequality, x is less than minus 1.19, and then I would do a u for the union, that's like the or part, and then I would do the second set, so this is x such that, x colon always, and then I'm going to write out that second part, x greater than 2.25, Sorry, 2.52. 2.52, and then you can close off those curly brackets. It's very rare. I hardly, if ever, see them ask for set notation for these kinds of questions, but just in case, that's how you would do it if you are asked. Okay, on to question 22. The diagram shows a sketch of the graph y is 2 sine x plus 60. So this is kind of like another transformation graph. And this is kind of similar to what I was saying before. Graphs of sine, cosine, and tangent actually came up in Unit 1, but they're often overlapped more with graph transformations. Whenever you get a graph like this, I look at the function here, so in my case sine, and I think about what does that look like under normal circumstances. So a normal sine graph starts at 0 and then curves up and then back down, and then we'll hit back at 0 again. And if you forget, you can always put sine of 0 in your calculator, and that will give you 0. So you know that you're starting off here. And you can put in sine of 90 if you want. And then you will see that sine of 90 is equal to 1. You will see that sine of 180 is back down at 0. Sine of 270 takes you to -1. And then lastly, sine of 360 takes you back to 0. This is kind of like where those sort of like important points are. The points where we cross the x-axis and the maximum minimum points. Now my graph has been transformed. So I'm going to look at this first one here, A. Now I can see outside of the function, I have this 2 outside of the function. So this is going to affect the y coordinates. Outside affects the y coordinates, inside affects the x. And if I think about this sine graph that I drew in blue, that went between 1 and -1. Well, that maximum there must have doubled, because if you are outside the brackets, you're affecting the y-axis. We do what we think we should do, so we times everything by 2. So that means that this point here is now at 2. So I'm going to put the y coordinate in as 2. Now let's think about what's happened to the x. Well, inside the brackets, we affect the x-axis, but we do the opposite to what we think we should do. And we are actually, instead of adding 60, going to subtract 60. Well, where was this point here, A, on my original function? It was here, this first maximum point. This is A on the original function, and that was at 90. So I'm going to subtract 60 from 90. 90 minus 60 is 30. And so what that means is that this point here must now be at 30. It's not necessary to draw it on the graph. I'm just doing that for demonstration's sake. Then finding the coordinates of point B, well, I can actually see quite clearly what the y coordinate is. The y coordinate is just 0. Now, where is that intersection point? Well, that intersection point must have been this point here, B, where I intersect with the x-axis. And that was at 180 on my original graph. Oh, sorry, that's not even the right one, is it? Sorry. What I've labelled on, the first point of intersection, that's actually going to be this one, isn't it? This is the point that was at 180 degrees. This point here, B, was actually the point that was at 360 here, B. So I'm going to do 360 minus 60, and that is going to get me 300. Okay, moving on to the next problem. So here we have some functions. First of all, I have a composite function. So I want f of g of 2. And so you're going to think of this like some little nesting dolls. The 2 goes into the function g. You get the answer, and then that is going to go into the function f. So we find the function g, and first of all, I'm going to put 2 in there. So I'm going to do 7 times 2, which is 14, minus 6, and I get an answer of 8. Oh, sorry, that's not the answer. 14 minus 6 does get you an answer of 8, but it's not the dotted line answer because we are only halfway done. 8, because this was g of 2. Now I need to work out f of that. So once you've worked out g of 2, now this needs to nest inside f. And so you're going to take this solution here, the 8, and you're going to substitute that into the f function where you see x. So now we are doing f of 8. And so if you put f into that function, you're going to do 5 times 8 all squared minus 10 times 8 plus 7. And that, you can just type it into your calculator, is 247. Now we are done. 247. Now we are looking for an inverse function. Inverse functions of linear functions, so like this g, are relatively easy. You would just write y is equal to 7x minus 6, flip around the x and the y, and then rearrange the equation to make y the subject again. For a quadratic, like f of x, which is what we have been asked to do, the inverse of f of x, this is a little bit more tricky. When you have a quadratic, you are first going to need to complete the square. And so this is an example of what I was saying at the beginning, like completing the square was actually in unit 1. But it overlaps with functions so much that I think that this is definitely a possibility. I think they will include some unit 1 stuff, particularly when it overlaps with your topics for unit 2, which in this case it does. And they're going to assume that you know it from unit 1, or at least you should know it from unit 1. So first of all, if you're looking for the inverse of a quadratic, you are going to complete the square. To complete the square, if you have a number before the x squared, which we do, we don't like that. So first of all, we factorize that out. So this is 5, and then I open up some square brackets, x squared minus, I'm going to divide this by 5 as well to get 2x, close off the square brackets and leave the 7 on the outside. Okay, once you've got it like this, we're going to complete the square on the thing inside the square brackets. So the 5 is going to remain, the square brackets remain, the 7 remains on the outside, and we can complete the square on this bit in the middle. So we end up with, in some round brackets, x minus 1. We divide this number here by 2 always to get this number, all squared, and then we subtract that number squared. So 1 squared is 1, so I'm going to minus 1. Okay, now we've kind of done the completing the square part, but I have something that looks a little bit untidy. What I want to do is expand out these square brackets. So I'm going to say y is 5, x minus 1, all squared, minus 5, and then that plus 7 is still on the end. Now we can collect together the minus 5 and the plus 7. So y is 5, x minus 1, all squared, minus 5 plus 7 is plus 2. Okay, once we've got the completed square, then I kind of go on to doing the inverse part, inverting the function. And to invert the function, we're going to swap around the x and the y. So I'm going to write x is equal to 5, y minus 1, all squared, plus 2. So where you see x, you write y, and where you see y, you write x. Now we want to rearrange this function here. So I'm going to slowly try and rearrange it so I can make y the subject. First of all, I'm going to subtract 2 onto this side. So I have x minus 2 is equal to 5, y minus 1 all squared. Then I divide through by 5. So x minus 2 over 5 is equal to y minus 1 squared. Now I can take the square root. X minus 2 over 5, all in a root. And remember, when you take a root of something, you have two solutions, one positive and one negative. Now this is equal to y minus 1. And then lastly, I'm going to add 1 onto the side. So I have 1 plus minus x minus 2 all over 5. And this thing here now is all equal to y. Okay, so we have successfully completed the square. The problem that we have is just the plus minus part. So they always want you to select one, either the positive or the negative. And which one you select will depend on the domain that they give you. They'll always give you this. So in our case, the domain for the original function f of x was x greater than or equal to 1. Now the domain of the original function becomes the range of the inverse. So in our case, the range, so the outputs is going to be y is, was it greater than? Yes, greater than or equal to minus 1. So if I want this function to be more than or equal to 1, what am I going to do? Am I going to add or am I going to subtract? I need to add, because if you have 1 and you add something on, you will end up with something more than 1. If you had 1 and you subtracted something, you'd end up with something less than 1. So the final answer is f minus 1 of x. The inverse is 1 plus the square root of x minus 2 all over 5. And we can go on to our next question. So here we have a similar shapes question. When we are looking at similar shapes, the same as we were doing originally, to go from one to the other in terms of the lengths, you multiply by some value k. When you are going to from one to the other in terms of area, you are going to multiply by some value k squared. It will be the same value, but you will square that. And then if you are going from the volume, you will multiply by k cubed. So if you remember the triangles that we had back down at question 1, when we were converting between the lengths, we had a value that we multiplied all of the sides by, and we've made sure that was consistent for any side that we were changing. If you are looking at an area, you end up multiplying by k squared. I think I will just sketch out a little example, just in case this is difficult. So if, for instance, I told you that this side length here was 3 and this side length here was 6, then you would tell me, well, we have multiplied here by 2. So this is like the conversion factor between the side lengths. So if I told you that this was 2, well, then you'd say, well, this must be 4. We times by 2. The area is a little bit different. The area is 2 times 3, which is 6. The area of this is 4 times 6, which is 24. So when we are converting between the areas, we don't actually times by 2, we times by 2 squared, which in this case would be 4. Now we could extend that again if we are given some volume. Let's say I tell you that the volume of this cube is 5, for instance. The volume is 5. Then because the conversion factor between the length is 2, the conversion factor between the area is 2 squared. The conversion factor between volume is going to be 2 cubed. So 5, in this case, times 8 would get us to a volume of 40. So that is why I'm doing this this k squared and k cubed. Because when you are converting between lengths, you have the conversion factor of k. Converting between the areas, you multiply by k squared, and then converting between volumes, you multiply by k cubed. And I think this is a really good example of what I meant by this is they could still include some indices and things like that in there. This is times k squared, and then times k cubed. So I need to work out what the value k is, and the easiest way I can see to do that is the area section, because the area is just a number, right? So let's see what the conversion is, and I think I'm actually going to see what we times by in this direction. I can see solid B is the smaller one, and I usually try and keep k as being a number bigger than 1 rather than less than 1. I think it's easier than getting a fraction. So I'm going to do 7776 divided by 486. And that is 16. And remember, this is not k, this is k squared. So if k squared is 16, well, what is k? K must be the square root of 16, which is 4. And so this is great. I've now worked out what all these k values are, and I can actually go and write those in. So I know that k is 4. So in terms of the height, just on the other side, we're timesing by 4. To convert between area, we're timesing by 16. And to convert between volume, we're going to times by 4 cubed, and 4 cubed is 64. Okay, so I want to work out what the height of this solid is. To do that, I'm going to need x. And so I think now I'm going to go down to the bottom of the table and start looking at the volume. So to go from this volume to this volume, we are multiplying by 64. So I'm going to write 64 times 2 to the power of x plus 4 is equal to 8 to the power of x. Now I'm trying to work out what x is. This is a difficult problem, but I can see that all of these are 2 to the power of something. it might be easy to see that 8 is 2 cubed, but 64 is also a power of 2, and you can do this by a little bit trial and error on your calculator if you need to. Try 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, and you'll see that 2 to the power of 6 and 64 are the same. So I'm rewriting all this because it's going to enable me to use the laws of indices in just a second. And so I'm going to write this as 2x plus 4, and this is equal to 8. Well, 8 is 2 to the 3, all raised to the power of x. Now I go ahead and use the laws of indices. So when we are multiplying, we can add the powers. So 2x plus 4 plus 6, I add those indices. I can multiply these two indices together. So this is 2 to the 3x. Let's simplify that out, that left-hand one. So 2 to the x plus 4 plus 6 is 2 to the x plus 10 is equal to 2 to the 3x. And so now I'm going to say that, well, because this is the same base, x plus 10 must be equal to 3x. And now I can go ahead and solve this. So I'm going to subtract x from both sides, take this over a minus. So 10 is 2x, and dividing through by 2, x is 5. Okay, great, we found out what x is. So that means I can come back up here and I can say that for solid A, this is 3 to the x, which is going to be 3 to the 5, because x is equal to 5, and 3 to the 5 is 2, 4, 3. So actually this here is 2, 4, 3. Now we were going in this direction to get k times in by 4, so to go back the other way, I'm going to have to divide by 4. So I'm going to have 2, 4, 3 divided by 4, and it says give your answer as a decimal. This is 60.75. And that is our answer. We can write this on our line. Okay, on to our last question, which is a vectors question. So we have most of this already labelled on the diagram. I always kind of do a little check. All of these are already labelled on. This ratio, however, is not, because to label it on would make it a little bit confusing for people. But I'm going to go ahead and do that. So AB is this length here, and that is 1 part, and BD is this length here, and that is 2 parts. And it is usually easier to convert these into a fraction. So I look at the total here. Well, in total there's 3 parts, so this is 1 out of 3, and then this other part here is 2 parts, so this is 2 out of 3. And then we're told that the point C on AB is such that OCE is a straight line. Use a vector method to find the ratio OC to CE. So we're told that this OCE is a straight line, and I want to know what fraction along the line have we gone when we get to C. So is O to C halfway? Is it a third of the way? Is it a quarter of the way? Is it 2/5? Something like that. Let's see what we can work out first. So I think it's going to be very easy to work out AB. I think it's very easy to work out AB. I think from that I will be able to get BD. And I think I can also get OE. All these vectors are important, so if you didn't know where to start on this problem, you can always pause the video now and see if you can just work out these. So for AB, we are going to go backwards along AO, so I want minus 2A, and then forwards along OB, so this is going to be plus 2B. And then for, now once I've got AB, I can also get BD. So remember this ratio here, it was 1 to 2. BD is twice as much. So it's double the length of OA, so it's just going to be minus 4A plus 4B. And then OE we can get by taking a route along here, and then up there. That's the kind of route we're doing. So this is going to be 2B plus BD, and BD is minus 4A plus 4B. And then lastly, plus DE, which we were given, that is 7A plus 3B. Now this is looking very messy. I do just want to simplify this. So I'm going to collect together all of the A's and collect together all of the B's. So collecting together the A's there, we have minus 4A plus 7A, which is 3A. And collecting together the B's, we have 2 plus 4 plus 3, which is a total of 9B. Okay, and so that's our kind of like useful vectors done. Now we can go on with the kind of proof or vector method part of the problem. And then to solve these problems, what you usually want to do is to get a vector and work out in two different ways. So I can see OC and CE. This is the ratio I want. So I'm going to go for OC, and I'm going to travel along two different paths. So first of all, going from O to C, I can see that I can go directly down here, this bit. So I'm going to say that OC is equal to some fraction of OE, because that's what I'm doing. I'm going down that blue line. That blue line is OE. But I don't want it to be all of OE. It's like a third of OE, a half of OE, an eighth of OE. This is actually what we want to work out, what that fraction is. We need to use a letter to represent the fraction. Now, if you want to, you can use X and Y. If it's more familiar for you, work through this whole problem with X and Y instead. But usually for these problems, we use the Greek letters lambda and mu. So we'll stick to the proper notation and use lambda in this case. So this lambda represents the fraction that we are along the OE line. Now, OE I actually know. We worked that out, right? This was 3A plus 9B. So let's go ahead and just put that in. So this is some fraction of 3A plus 9B. Now, that's one way of getting from O to C. I need to go down a different path. And I think the easiest path I can see, although you probably could choose other methods, is to go from O to A and then from A to C. So I'm going to go along this path here and then along there, and I'm going to land at C. And so this is also OC. This is OC via a different route. Here I'm going to go along OA, which is going to be very easy to fill in a second because that is going to be 2A. And then I'm going to C, so I don't want all of AB, but I want a fraction, a bit of AB. And I don't, again, know what that fraction is because I don't know whereabouts C is placed along that line. And so I'm going to need another letter here to replace it with a fraction. And this is where I'm going to use mu. So it's some fraction of AB. But again, you could use X and Y or something else. Just don't use A and B, obviously, because that will be confusing with the vectors. Now, again, I'm going to substitute these in because I actually know what both of these vectors are. So OA is 2A. And then I want some fraction of AB. And AB is minus 2A plus 2B. Okay, this is looking pretty good now. What I have is I have the same vector two different ways. And what we are going to now say is because this is the same vector, however many A's we have over here must be the same as how many A's we have over here. So for instance, if this red vector was like 10A plus 2B, then it means that the green vector must also be 10A plus 2B. They need to match because they are the same vector. So what I need to do is look at the vector on the left, the red vector, and ask, well, how many A's are there and how many B's are there? And then I will do the same for the green. Now for the red one, it is easier because all we need to do is expand that bracket. So I'm going to say OC is 3 lambda A plus 9 lambda B. And so that is how many A's and how many B's we have. We have 3 lambda A and 9 lambda B. And that's going to have to be the same as the green vector. But the green vector is harder to see right now how many A's and B's there are. Let's first expand the brackets also. So this is going to be minus 2 mu A plus 2 mu B. Now I can see I've got some A's and some B's. The B's are easy. I've got 2 mu B here, and so that must be equal to the 9 lambda B in the red. The A's are a bit harder because we've got them split up over 2, and we're going to have to factorize A out of these two parts to see how many A's there actually are. So I'm going to write OC is equal to 2 minus 2 mu A. I factorize A out the first two terms, and then I have plus 2 mu B. So now I can see very clearly how many A's and how many B's I have in both the red and the green, and I'm going to use that to set up a simultaneous equation. So in the A's, I have 3 lambda A must be equal to 2 minus 2 mu. 3 lambda is equal to 2 minus 2 mu. And then in the B's, we have 9 lambda. Delete. We have 9 lambda is equal to, and that is going to be equal to 2 mu. So the amount of B's must also be the same. Now we have a simultaneous equation. You could go ahead and solve this simultaneous equation and find both lambda and mu. We actually only need one of them. What I'm interested in is this red thing here. I want to know what fraction this was, and this was lambda. What fraction of the way are we along the OE line? So to work out lambda, what we're going to do is rearrange this second thing to get mu, and then I'll substitute that into the first. So I'm going to rearrange this to get mu is equal to, and to do that, I just divide through by 2. So mu is 9 lambda over 2. And then I'm going to take this thing, because this is mu, and just substitute it into there, and I'll be able to solve. So I have 3 lambda is equal to 2 minus 2 mu, and we just said mu is 9 lambda over 2. So now I'm going to solve this equation for lambda. First of all, I can expand that bracket, which will just cancel the 2's down. So I have 3 lambda is 2 minus 9 lambda. Now I'm going to add 9 lambda onto the other side. So 3 lambda plus 9 lambda is 12 lambda is equal to 2. And then I'm just going to lastly divide through by 12. And so I have lambda is equal to 2 over 12, which is the same as 1 over 6. And we have found lambda. Lambda is a 6. So that means is that C is 1/6 of the way along. So this, I'm going to go back to red because it was in red. This is 1/6 of the way along the line, which means that this second part here must be 5/6 of the way along the line. 1/6 must match with 5/6 in order to make the whole. And so now we need to go back from fractions into ratios. So this is 1 part and this is 5 parts. 1 part to 5 parts of the whole thing. Now let's just check the ratio that we were asked for, just to be certain that we are correct, because sometimes they ask for the ratio OC to OE. So we just check. So OC is the short part here. Yes, this is definitely 1 part. CE is this second part here. Yes, this is definitely 5 parts. So the ratio is 1 to 5. And that can go on my line here. Now that is a pretty difficult question. I think that is pretty much as hard as vectors gets. And if you see this thing saying vector method, whenever you see something that says use a vector method, that is when your alarm bells should go off, that this is this difficult kind of question that involves a proof. And more often than not, you'll have some kind of simultaneous equation to do in there, and then equating coefficients. If you found it hard, just pause the video, rewatch it again, and I'd recommend, if you struggle, to replace lambda and mu with x and y in your workings out. It might make things just look a little bit more familiar to help it kind of click into place. I hope that that was helpful, and I wish you the best for your exams. As I said, I did my best to choose questions that matched up with the Unit 2 specification, and I hope that it is a very nice paper for everyone. Okay, and feel free to let me know if you have any questions or comments, then you can type them below, no problem, and I'll get back to you.